This is a single grain of sand. Now imagine every single one on every beach in every desert buried beneath every ocean. What do you think is the total number of every single grain of sand in our planet? I'll tell you this, it's a lot. Like that number is more than everything you can see right now. It's more than the number of insects in the world, the total number of every house ever built. It's even bigger than the total number of seconds since the Big Bang. Now, do you think that this number, this simple line of math, or should I say tower, is bigger than that? Because in a previous video of mine, I compared its little brother to another massive number, and against all odds, it won. But this feels different. This is the whole world. There is no way a few symbols on a screen are bigger than our entire planet, right? To find out, we need to do two things. First, quantify our planet. What is this unimaginable number? And second, build the tower that might dwarf it. Let's call the total number of sand a mountain, and then this number a tower, because that's what it is. Let us first quantify our mountain. After all, we can't run an experiment without measurements. Right now, the best estimates from geologists and physicists give us this number, 7.5 quintillion. A quintillion is an almost meaningless word. Let's give it meaning. If you had 7.5 quintillion seconds, you'd travel back in time 240 billion years into the past. The problem is that the universe is only 13.8 billion years old. Did that give you any idea of how big this number is? Because this number isn't just big, it's cosmologically big. It's so big that it is a unit of measurement that makes our planet's history look like a blink. Now that we know the number to quantify our mountain, and we know how large that number is, now we must build our tower, step by step, and then answer a question. Can anything, even in the abstract world of pure math, possibly climb this high? To find out, we need to know what this tower is and why it looks the way it is. This is called tetration, and in my previous video I plainly explained what tetration is and how it works, but if you haven't already watched it, I'll give you a brief explanation. We start simple, the foundation of the tower, 3 raised to the power of 3. This operation is simple. Just like exponentiation, you'll be multiplying the number with the power, which means 3 times 3 times 3, and that's 27. Compared to our mountain, it's nothing. This is just like you versus Elon Musk's bank account. Yes, that difference, which makes step 1 humble. Now, step 2, we take that 27 and we build the next floor, 3 raised to the power of 27. This is where ordinary exponentiation shows its power. The result? 7.6 trillion. Now that's a serious number. Now if you put it next to our mountain, see this? Step 2 of our tower is in the trillions. Our mountain is in the quintillions. A quintillion is a trillion multiplied by a million. So our mountain is still 1,000,000 times larger. The tower is climbing fast, but the mountain still looms impossibly high. Now, step 3. This is where we leave any physical analogy behind. We are no longer calculating 3 raised to a big number. Now, we are calculating 3 raised to the power of step 2's entire result. 3 raised to the 7.6 trillionth power. At this point, logic has left the chat. We cannot write this number. I repeat, we cannot write this number. No computer can hold it. So what's the use? Yes, we cannot write the number, but we can ask a different, more revealing question. Not what is the number, but how long is it? How many digits does it have? The answer, approximately 3.6 trillion digits. Just the length of the number is 3.6 trillion places long. For example, if the number is rounded up to 3.6 and the rest is zeros, we will have more than 1 trillion zeros. And this gives us our final clean question. We have a mountain of 7.5 quintillion grains, and we have a tower whose mere description is 3.6 trillion digits long. How do we compare a quantity to a length? What's the exchange rate between a grain of sand and a digit? We have 3.6 trillion digits. Let's imagine writing them out, and let's assign a grain of sand to each place value. The rule is simple. For the digit in the ones place, that's 1 grain. For the tens place, that's 10 grains. For the hundreds, 100 grains. This isn't about the digit's value, like 5 or 7, but about its positional power. So a digit in the thousands place represents thousands of grains. A digit in the millions place means millions of grains. A digit in the billions place, billions of grains. Now remember our mountain. All Earth's sand is about 7.5 quintillion grains. Look at this. A single digit in the quintillions place of our tower's number would already be worth 1 quintillion grains. It's already in the same league as our entire planet's sand, and we have trillions of digits to account for. But we don't have just one digit in the high places. We have digits in quintillions, quadrillions, trillions, billions, all the way down. When you add the sand for every single digit's place value in this 3.6 trillion digit long number, the pile of sand needed to pay for writing out 3 tetrated to 4 is 200 billion times more massive than the entire Earth's supply. 200 billion, not million. This isn't a bigger pile, this is a different category of object. 3 tetrated to 4 is so large that using our planet as the unit of measure, you would need 200 billion copies of Earth just to hold a written copy of it. The mathematical idea doesn't beat reality, it redefines what big means. So what have we actually discovered? What this video really means is that certain things that looks impossibly large can get dwarfed by something so deceptively small. Who would have thought that this simple math is bigger than something so large? Well, I would have because I made it, and so will other seasoned mathematicians and students alike. But if you ask a kid, someone that isn't that literate or a random stranger, do you really think that they will say the equation wins? I mean, if you walk outside right now and look at your backyard, you will see sand, and if you start digging, no matter how many sand you dig up, it's still no match for a simple equation. Now think of every other sand in every single street, block, state, country, or even continents. There's even still sand in the ocean, and that's still not enough for this simple equation. Man, it's still hard to believe. This was the first experiment in math versus reality, and it raises an even wilder question. What other realities can we test? And before you go, try to subscribe. It helps me and will definitely help you too. Have a nice day.